Welcome back to another explainer. Today, we're talking about an absolute game changer in astronomy. We're looking at how NASA's upcoming Nancy Grace Roman Space Telescope is going to completely revolutionize our understanding of the universe, especially when it comes to hunting down new planets. If you follow space exploration, you know we've made some pretty incredible strides in finding exoplanets lately. But Roman? It isn't just a step forward, it's a giant leap.
All right, let's just jump right into it with this mind-boggling number, 100,000. Roman is actually predicted to discover a staggering 100,000 new transiting exoplanets. Just take a second to let that sink in. Up until now, humanity, working together, using all of our various missions and observatories, has found roughly 6,300 exoplanets in total. Roman is about to multiply our entire known catalog of worlds by a factor that's honestly kind of hard to comprehend.
To put that sheer scale of discovery into perspective, think about NASA's legendary Kepler mission. Kepler fundamentally transformed astronomy by proving that planets are actually more common than stars, and it discovered about 2,800 confirmed planets in the process. It was a total legend. But compared to Kepler, the Nancy Grace Roman Space Telescope is about to literally drown us in an ocean of new planetary data. It's shifting us from taking a small, localized census to doing a massive, galaxy-wide sweep.
So, let's dive into Roman's wide-angle revolution and see what this new era of big data is all about.
You're probably wondering right off the bat, how exactly does Roman differ from our famous existing space telescopes like Hubble or the James Webb Space Telescope? Those observatories are already doing incredible science, so what gives Roman its unique superpower?
Well, you might be surprised to hear that Roman's primary mirror is exactly the same diameter as Hubble's, 2.4 meters across. But here is the critical distinction, the field of view. While Hubble and Webb operate a bit like incredible telephoto lenses that stare deeply and precisely at very small targets, Roman uses that identical mirror to act as a wide-angle survey camera. Its field of view is at least 100 times larger than Hubble's. That means a single exposure from Roman covers a massive swath of the sky that would take Hubble roughly 100 separate, time-consuming shots to map out.
It's really the combination of these technical advantages that makes it so powerful. Roman is going to be parked 1,000,000 miles away at the L2 orbit, which is the same neighborhood Webb hangs out in. From there, it uses its crisp near-infrared sensitivity to peer straight through thick clouds of cosmic dust. And because it captures 100 times the area of a Hubble image in a single shot, it can monitor hundreds of millions of stars simultaneously for the tiniest changes in brightness. That's exactly how we're making the jump from a few thousand known planets to 100,000.
Which brings us to the actual cosmic detective story, the two main methods Roman will use to catch these hidden planets.
Because, as you know, finding an exoplanet isn't like snapping a quick photo. Planets are incredibly faint compared to the blazing stars they orbit. So the first trick up Roman's sleeve is the transit method. This is how it'll find the vast majority of its new worlds. It basically involves staring at a star and waiting for a miniature eclipse. When a planet crosses or transits in front of its host star from our point of view, it temporarily blocks a tiny fraction of the starlight. By tracking that periodic dimming, astronomers can prove a planet is there. It's a fantastic way to find large, hot planets that orbit super close to their stars.
But Roman doesn't stop there. It's also using a fascinating technique called gravitational microlensing, which plays right into Einstein's general theory of relativity. When a foreground star randomly aligns with a distant background star, the foreground star's gravity actually acts like a cosmic magnifying glass, bending and temporarily brightening the background star's light. And if that foreground star has planets, they add their own tiny gravitational distortions to the light. Microlensing is brilliant because it catches the planets the transit method misses, worlds orbiting much farther out, or even rocky planets as small as Earth and Mars.
So what exactly is Roman going to find? Roughly 3/4 of these 100,000 transiting discoveries will be gas giants like Jupiter or ice giants like Neptune. But the remaining 25%? That's where things get really fascinating. Most of these are going to be mini-Neptunes, planets between 4 and 8 times as massive as Earth. What makes them so mysterious is that there's absolutely nothing like them in our own solar system, and Roman is about to hand us tens of thousands of them to study.
All right, let's talk about our new galactic hunting grounds, pointing deep into the Milky Way.
Because simply finding planets is only half the battle, right? Where we point the telescope is just as important. Currently, most of the exoplanets we know about are relatively close to Earth. For instance, the TESS mission scans for worlds about 150 light-years away. Even Kepler mostly stayed within a 2,000 light-year radius. But Roman? It's looking an astonishing 26,000 light-years away.
peering straight into the dense, chaotic heart of our galaxy, the Milky Way's central bulge.
NASA exoplanet researcher Elisa Quintana actually hit the nail on the head regarding why this matters so much. She said, "Our galaxy is home to a variety of different environments, but when it comes to hunting for exoplanets, we've really only explored one, our own neighborhood." By pushing way out of our local bubble, Roman is going to finally let us compare planetary systems across wildly different galactic environments.
So why stare right at the galactic bulge? Well, it's packed tightly with stars that are much older than the ones in our local spiral arm. More importantly, they have a completely different chemical makeup. They're loaded with heavy elements like silicon and oxygen. Since planets form from the exact same leftover material as their host stars, studying these heavy element-rich areas will teach us how planet formation changes depending on your zip code in the galaxy. We already suspect that stars with more heavy elements host more giant planets, but Roman is finally going to give us the massive data set we need to prove it for sure.
This all builds up to what we can call the ultimate planetary census, complete with rogue planets and, honestly, free science. Because Roman is taking this sweeping, massive overview of hundreds of millions of stars, it's bound to spot some incredibly exotic stuff. Thanks to how sensitive that microlensing technique is, Roman is predicted to find around 250 rogue planets. These are actual worlds, some as small as Mars, drifting in the pitch black of space, totally unbound to any host star. Catching these free-floating worlds is going to give us huge clues about the chaotic gravitational billiards that happened during the early days of a solar system.
And honestly, my absolute favorite part of this mission design is what astrophysicist Jennifer Yee calls free science. To find those microlensing events, Roman has to stare continuously at millions of stars to track precise changes in their brightness. Well, guess what? That is the exact same data you need to find transiting planets. So Roman is going to discover its 100,000 transiting worlds simply by combing through the very same observations it's already making for its primary surveys. Talk about an insanely efficient use of a space telescope. So when does this incredible era actually kick off? Well, Roman is slated to launch on a SpaceX Falcon Heavy rocket around late 2026 or early 2027. Once it's up, it'll travel that million miles out to the L2 point, run its calibrations, and immediately begin delivering a massive deluge of public data. And I do mean public. The data will be available to scientists and everyday citizens right away. So anyone, anywhere, can join the hunt for these 100,000 worlds. Which leaves us with one incredibly exciting question. As we step into the era of Roman, where we go from knowing a few thousand planets to suddenly having a massive galactic census, hidden somewhere within those 100,000 new worlds, orbiting quietly in the habitable zone of an ancient star, will we finally find a pale blue dot just like Earth? The data's coming. We just have to be ready to look. Thanks for joining me on this explainer, and keep your eyes on the stars.